Hello, good morning, students. So we are starting to continue with chapter 4, and we're in a section called redox reactions, which is short for oxidation reduction reactions. This is going to be covered in 2 videos. The first part discussing the basics and then balancing redox equations. This is an important section because it's critical for many everyday phenomena such as the use of batteries and how batteries work. So the main thing that's happening in a redox reaction is you have a transfer of electrons. So you can consider magnesium, which is a group 2 metal, and it can lose 2 electrons to become a cation, Mg2+. Where do those 2 electrons go? It goes to an element that can receive 2 electrons, here oxygen, which is generally in the form O2, but for simplicity, we're just showing O. It can gain 2 electrons to become its common anion. So the main point of a redox reaction is you're having a transfer of electrons. And in this case, we're forming this magnesium oxide solid, which is an alternating array of cations and anions. So there are 2 things that go hand in hand in a redox reaction, in oxidation and reduction. The oxidation step is the loss of electrons. So for magnesium, magnesium's losing 2 electrons, so magnesium is being oxidized. And who is he being oxidized by? By oxygen. So in this case, magnesium is oxidized and oxygen is the oxidizing agent. Also, oxygen is being reduced because it's gaining electrons. And so the substance that's reduced is O. And I already mentioned O is the oxidizing agent. But the other thing that I should tell you is magnesium's doing the reducing. So magnesium is called the reducing agent. So just to make it clear, the guy that's oxidized is reducing the other guy. So the guy that's oxidized is the reducing agent. The one that's reduced is the oxidizing agent. And something that you can see, you're going to have to be able to tell what is being reduced and oxidized in a redox reaction. When you see a gain of oxygen, for example, magnesium adds oxygen, magnesium's being oxidized. That's one easy way to remember it. Another one is this little mnemonic, Leo the lion says grr, GR. So what that stands for is a loss of an electron or loss of electrons is an oxidation, and a gain of electrons is a reduction. So let's look at a classic example of iron rusting. You've seen this in your everyday life. Iron, which is the main component of steel, can be oxidized by oxygen. So iron is oxidized. Here it's in its neutral solid form, and it can lose electrons to become iron 2+. I'm sorry, this is iron 3+. I apologize. Iron 3+, you can see that with the 3 here. Oxygen is going to gain electrons and become O2- in this ionic compound to generate your iron oxide, which is rust. So look at this big picture here. Here's your iron, the metal iron, your steel. Here's the water. That's why you normally see things rusting after rain, because you do need some water to help facilitate this electron transfer. And just some little bits to notice, I won't test you on this. The anode is where the oxidation occurs. So iron here, Fe solid, is being chewed up and converting to its ion form. And then it can combine with oxygen to generate your iron oxide rust. The cathode is where the reduction occurs. These are important when you start looking at batteries. So let me just help you determine when things are being oxidized or reduced, because it's not always obvious. You don't have this simple case all the time. Something that we need to introduce is called the oxidation number, abbreviated ON. When the oxidation number changes for something, that means a redox reaction occurred. So when you have an actual oxidation, for example, iron in its neutral form, the oxidation number is just 0 for something in its neutral elemental form. If it increases, like it did here, increase to iron 3+, you have an increase in oxidation number. That means you had lost electrons because you went from 0 to 3+, for example. So that's your oxidation when you see an increase in oxidation number. If you see a decrease in oxidation number, so here we have iron, it was 0 because O2 is in its neutral elemental form, and it goes to 2-. And when we talk about oxidation numbers, we put the negative first, so we say it's a -2 here. And so that number decreased or reduced, so that's your reduction step. So that's a really easy way to tell, but you need to be able to assign oxidation numbers. So I'm going to help you do that. Here's another classic example. This is a really beautiful experiment to do. You have this copper wire, and if you put it in a solution with silver ions, say silver nitrate, that's soluble in water, you will undergo and observe a redox reaction where the copper starts getting chewed up and it's forming copper ions, and the silver ions that were floating around in solution is now plating out. Here they kind of look pretty crystalline, but they'll plate out as silver solid. So originally you have this, your copper wire. Notice the copper solid, that nice array, silver ions in solution. But over time, the silver becomes solid, and you can see them stacking here, making these little fringes here. And then copper starts becoming copper 2+ in solution. The reason why it's blue and it started out colorless is because copper 2+ is blue. Okay, so let me go over how to determine oxidation numbers. I have a list of rules, which you'll see in the next slides, but I wanted to show you and demonstrate this. So what we're going to do are these 4, and I'm going to do this on the board. So we have potassium, and it's metal, so that's a solid. We have sulfur trioxide. We have nitric acid, which is HNO3. And then we have phosphate ions, PO4 3-. So you guys can try all of these with me. I'm going to just show you this on the board so we can go through each of these. Anytime you have something in its elemental form, like a metal in its solid form, or say F2, I2, Cl2, Br2, N2, those are always going to have an oxidation number of 0. And I like to put the number on top just to help me track it. If you have a neutral compound, I'm just going to give you a tip. All of the oxidation numbers add up to 0. So for this to help us determine them, we need to know at least one of them. One thing that you can be sure of is oxygen, in our case, in this class, is always going to be -2. There are cases where it's -1 in peroxides, but for us, it's going to be -2. Sulfur, I don't know what it is. It could be a variety of numbers. So I'm going to let this be X. But what I do know is the sum of all of these, the X and 3 oxygens, has to add up to 0 because this is a neutral compound. There isn't a big charge like there is with the phosphate ion. So I'm just going to add it up. X -6, so notice I did -2 times 3 equals 0. So X equals +6. So that tells me that the oxidation number of sulfur is +6. So remember why we're doing this. Here I'm showing you isolated cases, but later we're going to have a situation where we have a whole equation and you need to look at oxidation numbers to determine if something's being oxidized or reduced. Okay, let's do this next one. So I already told you the rule that O is -2. Another rule is H is +1 for our purposes. I don't know what N is, so that's X. I know they all add up to 0, so I'm going to do 1 + X -6, -6, -2 times 3 equals 0. So X equals plus 5. So that means the nitrogen here has a plus 5 oxidation number. So our last one, it's not a neutral compound. It has a real ion charge. This is phosphate, the polyatomic ion. All that means is all the oxidation numbers now add up to the overall charge. The overall charge isn't 0, it's -3. So I know that O is -2. I'm going to let P be X, and they're all going to add up to -3. So X minus 8, 8 because -2 times 4 equals -3. And then X equals plus 5. So for these sorts like nitrogen, phosphorus, you cannot ever be sure what they are. You have to do this method to figure it out, because they could be a variety of numbers depending on how they're reacting. So I will go through and show a little bit more about the rules that I just went over. Anything in its elemental form is 0. Just a standalone ion, like I was showing on the previous slide, copper 2+ or silver plus, the oxidation number is its charge. And then I already mentioned the sum of oxidation numbers in neutral compounds is 0, but for a polyatomic ion, it's the ion charge. Here are specific oxidation numbers. Group 1A will be +1, 2A is +2. H, I mentioned, is +1. Sometimes it could be -1, but I won't do that in this course. Oxygen will be -2, and halogens are usually -1, but sometimes it could be something different if they're bound to another halogen or an oxygen. Okay, so let me show you just some real applications to this. Here's our common battery. We have manganese oxide paste with ammonium chloride and graphite powder. There's a graphite rod that acts as your cathode. You have a spacer and a zinc case that acts as your anode. So you have these two oxidation and reduction reactions occurring to give an overall reaction here. My whole point in showing this is that in this, you have a transfer of electrons. That's how you generate electricity, the flow of these electrons. The other really amazing application is in the generation of lithium ion batteries. So these are super lightweight. You guys use them in your phones, in certain electric cars, just all over. I just wanted to mention, because the Nobel Prize was given in chemistry to these 3 scientists that over the years, just based on the contribution to society this work had done, they won the Nobel Prize. And so for the lithium ion battery, similar concept, you have a metal casing, an anode and cathode, a separator, an electrolyte to help allow for a flow of, it depends, it could be charged particles, it can, it's generally charged particles. And you have a wire where you can have the electron flow and a current generating. Okay, so I won't go into the charging and discharging, but there's a really cool YouTube video that's not very long and is just really fun to watch to help you understand how your lithium ion battery works and how it recharges, why you do need to plug it back into the wall. The other thing I want to mention is the use of lithium ion batteries in the Tesla. So this is a very popular electric car right now. Here's a AA battery. This is the size. You know, the size of a AA battery is quite small. Use them in toys, clocks. Here's a lithium ion battery, not that much bigger. Here's a module of 444 of them. And look at the Tesla. This is the battery pack. You take 16 modules, which ends up being about 7,000 batteries, and that's the total Tesla S battery pack. So I don't know if you realize, but really in these electric cars, it's just stacks of batteries here. So you can see it here live, and they're showing that the lithium equivalent is about 15 pounds even though this entire pack weighs 1,200 pounds. Okay, I'm going to stop here. Next time we are going to go over how to balance redox equations.